Right. So I hope you understood the little part we have completed from the chapter Gravitation. So we are going to continue from the point where we left off in the live class. So we were talking about acceleration due to gravity. What was this expression? It was gm by r squared, right? Where this me and this is re, that is radius of earth, and me is the mass of earth, right? And following into that, we also decided to know how g will be affected. And there are 2 points regarding cbsc point of view, that is as per your textbook, and extra 2 points which is respect to NEET or entrance topic. So one is how the variation of acceleration due to gravity happens due to the effect of altitude. That we derive two equations, right? Which is one, g dash is equal to g divided by, g divided by bracket 1 plus h by r whole square, or g dash is equal to g into 1 minus 2h by r. These were two expressions, right? Now the next topic which we are going to deal with is how the depth, that is how much or how depth is going to affect the value of acceleration due to gravity, that is due to depth. So we are going to derive that one. Okay, so write the heading as effect of depth below the surface of earth on acceleration due to gravity. So for that we are going to assume this is our earth, right? And we are going to consider another concentric section of earth, right? And let's say there is a mass m which is positioned at a distance or a depth d from the surface, and let's say the total radius of earth is r. This much clear? So we are having a small mass m, and this mass will be experiencing a force only due to the inner sphere, not due to the outer sphere. I hope you know, remember that, right? Let ms be, that is capital ms be the mass of the smaller sphere, right? And me is the mass of earth, right? Clear? And r is the radius of earth. Then what I can talk about ms by me? You know mass is equal to volume into density, right? So I will write volume of earth, not earth, it is only the small section, right? So let us talk it as volume of the smaller sphere into density of earth divided by volume of entire earth into density of earth. These two can be cancelled out. So we can just write mass of the smaller sphere by mass of the earth is equal to volume of the smaller sphere by volume of earth, right? Now what is the volume of smaller sphere? It is 4 by 3 pi. What is the radius of the smaller sphere? It is r minus d. This much section is d, so this distance will be r minus d. So I will write it as 4 by 3 into pi into r minus d whole cube divided by 4 by 3 pi r cube. That is the volume of earth, right? So I can cancel these things. So I can write ms by me is equal to r minus, or here itself I will write, I'll just rub it off, r minus d whole cube divided by r cube, right? So now we can talk about the force which is exerted on small m, right? Let's say I am going to write this as f of d because it is at a distance, the mass m is at a distance d. The force experienced by this mass is due to the smaller mass, right? So I can write it as g into ms, that is the inner sphere or the smaller sphere, into small m divided by the distance between the mass and this one is what? R minus d. That's r minus d whole square, right? Clear? Now from this expression, this expression, can I write ms is equal to me into r minus d whole cube divided by r cube? Yes. Now I am going to substitute this value over here for ms, so that this becomes g into me into r minus d whole cube divided by r cube whole divided by r minus d whole square, right? So out of this, these two guys I can cut one term, so it becomes g into me into r minus d into small m divided by, this m I messed up now, divided by r cube, right? Clear? Sorry. Now from here, let us keep this equation. I know that for any force experienced by the small m is actually its weight. So I can write f of d is equal to mg dash. Why did I write g dash? Because g is the acceleration due to gravity on the surface of earth. I am going to take a point which is below to the surface of earth. There the acceleration due to gravity might be mg dash, right? The force experienced by this mass over here is equal to mg dash, right? So I can write here m into, right? So this, okay, sorry, I can replace an FD as this one, mg dash is equal to gme r minus d into m divided by r cube. So I can cut this m. So I get an expression for g dash as g dash is equal to g me r minus d divided by r cube, right? Now what is gmb by re cube? I can write this as r squared into r, right? So gme by r squared, that is acceleration due to gravity on the surface of earth, which is g into r minus d by r, right? That I can just rearrange and make it as 1 minus d by r. This is the value or expression for acceleration due to gravity at an inner section of earth which is d distance from the surface. That is, at a d distance from the surface or depth from the surface of earth, the acceleration due to gravity is g, which is the acceleration due to gravity at the surface into 1 minus depth by radius of earth. This expression is very important in the case of your board exam sections or not your school examination. Now, the next 2 points which we are going to talk is purely based upon entrance topic. That is third effect on the change of acceleration due to gravity, which is effect of shape of earth. Effect of shape of earth. Right. In all the above cases, we assume that the earth is perfectly spherical, right? But we know that the shape is ellipsoidal, right? That is, it is bulging at the equator, right? Here, like this, not in the completely oval, but little bit oval, right? And it is flattened at the poles, right? This is actually the shape of earth, right? So the equatorial radius which you talk about, this one, is greater than the polar radius, right? And we have found that g is actually inversely proportional to 1 by r square, right? So it can be said that g increases because in the equator section, right, it increases from the equator to the pole. See, here r is greater, so the g will be less. Here the r is less, so the g will be greater. So I can say from equator to the poles, g's value increases, right? That is, g is minimum at equator and g is maximum at poles. This you can study by yourself, okay? This is very easily asked in school examination also, but in school examination it is not mentioned that it is due to the shape of earth. Just mention that the g is minimum at equator and g is maximum at poles. So I am telling you why it is so. Clear, right? And the third effect on the acceleration due to gravity is effect of rotation of earth, right? Effect of rotation of earth. That you can just know that g dash is equal to g minus r omega squared cos lambda. This is an expression which depicts the relationship between acceleration due to gravity and what do you say as sorry you say as what acceleration due to gravity and rotation. So I will tell you by a pictorial representation. Again, I am telling you this is not there in your syllabus, right? This is our earth, right? Earth is rotating with velocity omega. This is the center of earth. Let's say there is a particle P, or right, the position of particle here, right? This is the radius of earth, right? So this particle will be having weight in downward direction towards the center of earth, right? I'm drawing a perpendicular here. Let's say this is M, right? So the force here mg, let's say this is lambda angle, right? So this is lambda, means this is also lambda, right? So mg means we are having mr omega squared, right? I hope you know this weight is balanced by centripetal force, right? So mg is actually equal to, if I'm telling you, so this is mg in this direction, the particle or the person will be experiencing a centripetal force, but that's only cos component will be there, right? Here it is alpha, so it is m r omega square cos alpha in this section. In this section he will be experiencing m r omega square. He will be perpendicularly thrown out, right? There. So here you can write mg dash is equal to, that is the force actually he is feeling, is equal to mg minus m r omega square cos alpha. You can cancel m. That's why you got the expression g dash is equal to g minus r omega square cos alpha. Clear? It's very easy. A particle is there, a weight perpendicularly downwards, right? He will be thrown out because the earth is rotating, right? He will be thrown out in this direction, right? So that force we are writing it as mr omega square, right? It can be depicted as centrifugal force also, because centrifugal force is outward direction, right? It's one component, we are taking it as mr omega square cos alpha. So net weight he is experiencing, or net force he is experiencing, I am writing as mg dash is equal to mg minus mr omega square alpha. From that I got a g dash is equal to g minus r omega square cos alpha, right? Sorry. Now there are two things you have to know. At equator, that is here, right, lambda is equal to 0 degree, right? That's why at equator you can write g dash is equal to g minus r omega square, and at poles lambda is equal to 90 degree, right? So you can write g dash is equal to g. These two things it is good to know for just NEET point of view or entrance point of view. Don't give much that much importance to this section in the school syllabus point of view, right? The next topic which you have to talk about is gravitational field. This is your school examination topic, okay? Gravitational field, right? Representation E, right? See, suppose actually if someone asks you the definition, before that I would like to explain you how it came up, right? So we don't jump to the definition as it is. See, we know that if there are two bodies m1 and m2, so they will be experiencing a law of attraction, right? And that force of attraction is given by F is equal to g m1 m2 by r squared, sorry, r squared, right? Clear? Where r is the distance between them, right? We have talked about it. Now this g m1 by r squared, I will call this term as gravitational field as E. That is, we may interpret E as the intensity of the gravitational field of mass m1, right? It is the intensity of gravitational field of mass m1, and can be defined as, if someone is acting, that is, I will explain it to you properly, I just want to complete the definition part. It can be defined as the force experienced by unit mass in the gravitational field of mass m1. I can talk like this. Suppose this is a cricket field, right? So there is a batsman, so he can have control, or he can play only in this field, right? So this is the area where he is hero, right? Similarly, if I consider a mass, right? Let's say the mass is m1, right? So this m1 mass will be having a field where it can exert force. So outside this field it can never exert any force. This area where it can exert gravitational force is known as gravitational field. That is in layman language. Clear? Right. So again I'm depicting. So suppose there is a point P here. Right. Let's say this point P is at a distance r from a mass, let's say m. Right. So this point P, if I bring a unit mass means mass which is having 1 kilogram as mass, right? So if I bring and keep 1 kilogram mass at this point P, so due to this small m mass at this point P, 1 kilogram will be having how much force? It will be experiencing a force of G m into 1 kilogram by r square force, right? That is, I can remove this one, right? So this is gm by r square. So this is the expression for E, right? So what is E? E is the force experienced by a unit mass, right, due to a mass m, right? Force experienced by a unit mass, right, in the presence of another mass m, then that is the gravitational field of m, right? Clear? Right? Clear? So what is gravitational force or gravitational field? It is the force, right? So I can even write it as force per unit mass, right? Again, remember what is F? F is G m. Let's say this in place of 1 kilogram, it is m naught by r squared, and we just say this gm by r squared is the gravitational field of mass m. So I can write F is equal to gm by r squared. I will write it as E into m naught, or I can write E is equal to F by m naught, right? So here I can say the definition: force experienced by a unit mass, right? Force per unit mass, right, when in the presence of the mass m, that is the gravitational field of mass m, right? Now comes the talk about the direction, right? The E, that is the gravitational field, is directed towards the source, right? And therefore in the vector form, the intensity of gravitational field at a point P due to this mass m at a distance r is the force experienced by a unit mass placed at P, right? So I will write this expression: E is equal to, I can write it combinedly, E is equal to, that is field at P, right, is equal to force per unit mass which is present at point P, F by m naught, is equal to G m by r square, right? This is the expression which we just combinedly have written. And I am telling you that electric field direction is always towards the source mass. What is the source mass here? This gravitational field is produced by this guy, not by this guy. This guy is experiencing the field, right? It is just like there is an area, that is this m is having an area around it, that is its gravitational field. Any mass which tries to enter here will be experiencing a field or a force of attraction due to this guy, right? If that coming mass is only 1 kilogram or 1 unit mass, which is very small as 1 m naught, if it is coming, then that mass is experiencing a force, or I can exactly talk it as gravitational field of m. Clear? Right? So an area, just like magnetic field, when you consider a magnet, there is an area where it can exert the maximum magnetic field, right? So outside that field, if you are having any iron bar, it will be not feeling any attraction. When that iron bar comes in the field of this magnet, then only it feels attraction. So this area which I have drawn is the magnetic field of this magnet, just like that. So every mass has its own gravitational field. Clear? Right? And that gravitational field is always towards the source, right? So this m and this is point P. I have brought a mass, unit mass here, right? So this E is always towards the source mass M, right? Clear? So usually you draw force of attraction which is given by this guide to in this direction now. So I will write EP in vector form is equal to minus gm by r squared r cap. R cap gives the direction, right? This is the direction. Usually we take it as positive, so this direction becomes negative. Clear? Negative indicates that EP is opposite to the direction of r vector. We always take r vector from the source to the destination. So this is from here to here. This is the direction of r vector, and E is in this direction. Clear? Right? So EP is equal to minus gm by r square r cap. R cap is just the direction, guys. Someone asks you the equation, you can write it as EP is equal to minus gm by r square. Minus indicates what? E is always opposite to the direction of position vector. Clear? So you see G is as well as capital E both are having what? Same direction. G is also towards the source mass. Similarly, that is towards the earth, right? Similarly, E is also Earth's field, right? Is also towards the earth's surface, or its earth's crust itself, right? And similarly, just like force, individual fields, sum of total or sum of field at point is equal to E1 plus E2 goes on. Just like superposition principle of force, electric field, sorry, not electric field, our gravitational field also can be added. Right, now again this much is the part which is there in your NCERT textbook level. Now we are going to take is all purely NEET or entrance topic, right? That is a gravitational field intensity due to spherical mass distribution, right? That is where and all, what and all values you have to understand. Again I'm talking purely based on NEET topic. Again, this is not there in your textbook. Suppose this is gravitational field intensity, only I'm talking about a sphere, guys, right? So there are two types of sphere, that is solid sphere and hollow sphere. Solid sphere means just like which is no, entire thing is having metal. Hollow sphere means this is full air, right? So first let us talk about for solid sphere, right? So how and all electric field is going to change. So for the first case, solid sphere, again this is an entrance topic. For solid sphere, for solid sphere, suppose this is the solid sphere. Let's say it is having mass m and it is having radius r, and this is the center. Let us consider a point P which is outside the sphere, that is distance is very greater than radius r. This is r, right? Clear? So electric field is outside, right? E out is equal to gm by r squared into minus r cap, right? Minus, I hope why I have taken minus, you, I hope you understand, right? And the second case, this is the first case, very easy to understand, guys. B, when r is equal to r, that means the point P is at the surface itself, right? So this is r, right? So r is equal to r. So again mass m, right? So E at surface is equal to gm by capital R squared. That becomes the distance here, right? Into minus r cap, right? Now what happens if this point is inside the sphere? Inside the sphere means C, right? That is, I'm going to consider this is the outer sphere. I'm going to consider another sphere here. Let's say the point P is here, right? And there's a distance r from the center, and this is the radius of the earth, and m is the mass, or not earth or the sphere which is solid in condition, right? So we have talked about it little bit while solving the case of our acceleration due to gravity, right? Due to depth, right? So inside the point or inside the sphere, that I can write it as E is equal to gm dash. Why did I write m dash? this mass, let's say the inner sphere is having mass m dash, right? Divided by distance is what? R squared and minus r cap, right? So ratio of the masses, right, that is the inner mass divided by outer mass or the total mass is equal to what? Density is same, right? So 4 by 3 pi r cube will be what? This is r cube. This guy is having 4 by 3 pi capital R cube, right? Density is same, so I need not write it again. So rho can cancel, this 2 cancels, so it becomes r cube divided by capital R cube, right? So I can write mass of the inner sphere is equal to outer sphere's mass or the total sphere's mass into r cube divided by capital R cube. Or I can replace this m dash with m, so I can say gravitational field is equal to gm, right, then r squared divided by r cube, then there is a minus r cap vector, whole divided by r cube, no, right? R cube or r squared? R squared, sorry. So 1 r squared cancels out. No, let me think, it is r cube or r squared. It is r squared itself now. So this is r cube, right? So numerator section, I'm sorry, it is r cube by r cube divided by this r squared. So 1 r cancels out. So you will get the electric field inside the solid sphere is equal to minus gmr, right? Or I can write it as minus r cap here divided by r cube. That is the electric field inside the solid sphere. Clear? So again I am depicting, this is purely based on what? Entrance topic. Now this can be even shown, electric field for a solid sphere. Someone asks you to show it graphically. So how would you show? This is electric field, let's say this is electric field and this is for air, right? So which value section I can say that E is maximum, at which point you are finding that E is maximum, right? You will see that all of the guys are negative, so the graph will be below, right here I will draw, the graph will be purely in this side. This much is clear, right? Now tell me in which section you will feel that the gravitational field will be maximum. It will be maximum at the surface, right? All the other points below to the surface or outer to the surface, the gravitational field will be less, just like the case of acceleration due to gravity, right? In acceleration due to gravity, the surface is having maximum g, and if you go up or below, g goes on reducing, right? I'm sorry for the disturbance. So initially, see, when E is outside, you will see that E is proportional to 1 by r squared. So exponential function, right? Let's take this is r side and this is for electric field, gravitational field. So at r, let's say you are having maximum value as minus gm by r squared, right? Minus g by m by r squared, right? Later on r is going on increasing, right? See, outer section, it is small r is greater, right, than capital R. So when denominator increases, the factor decreases. So, and also in exponential way. So this becomes the side for what? E out. This is E out section, right? Whereas in E in, you can see in E in, right, you can say that R capital at this R is reducing, right? Even that section you can see E in is inversely proportional to capital R cube, right? Again the denominator section is quite large, in or also in what cube section. The other sections it is only square, right? That's why again cube, right? So you are writing not in an exponential function, right? Clear? So this is how the graph comes out. Right, now the same section I can talk about in the case of spherical shell also, right? For spherical shell, So next heading is for spherical shell. Shell means it doesn't have anything inside. Clear? Right. Now, that is again just like the previous case. In the case of shell, I will take a point which is outside. Let's P point. This is R. This is capital M mast and R radius sphere. So E out is equal to Gm by R square with R cap as negative. Right? This is the condition when R is greater than capital R. Right? Just like the previous guy. That is just like the solid stage. Now, what happens when E naught is, what is not E naught? When the surface is considered, right? That is when R is equal to capital R. That is also just like the solid, that is G, that is I can just write it as E surface is equal to Gn by capital R squared minus R cap. Now, the problem comes regarding when you're considering a point inside. Guys, you are talking about a sphere which is what? Hollow. Hollow means at that point there is nothing to talk about mass or any section. So nothing is there, right? So electric field is equal to 0 here in a hollow sphere. Not electric field. I am talking about electric field again and again because this topic same comes in the case of electric field section in the 12th class. That's why it is coming again and again. I'm extremely sorry about it. Right, so inside there is no gravitational field. So the same section, so the previous graph I can repeat for 2 points, right? One is at surface and the other is outside. So the graph here to here is same, right? R. The other case, the 0 means there is no gravitational field, so I will draw like this. So this is maximum, that is minus Gm by R square, right? That is at the surface. This is for outside. Inside the gravitational field is 0, dead, right? So this gives the relationship between E and R in the case of a hollow sphere, right? And similarly, someone asks you to depict the graphical representation of G, that is acceleration due to gravity. That also can be depicted. At capital R, that is at the surface, it will be having the maximum gravitational acceleration due to gravity, right? So this will be maximum, goes on increasing, then, right? Clear? This is the graphical representation of G. So at right inside, gravitational field is less. As you go to the surface, the gravitational acceleration due to gravity is less, or I can say 0. As the surface reach, the gravitational field is causing an acceleration due to gravity which is maximum, and then as you go to the upper surface, G goes on decreasing. This is how you depict the graphical representation for G also. This is there in your textbook. Okay, clear? So this much is very important in the case of gravitational field. And actually there is another thing, gravitational field intensity to a thin uniform ring, but I would expect to take you or take the same topic in the case by relating it with the electric field in the next year, 12th. So the derivation part taking here is not sensible enough. Okay, this much clear. So we talked about how the gravitational acceleration due to gravity changes with the height, due to depth, due to its shape, and due to its rotation. And then we talked about in detail about what? We talked in detail about spherical shell and solid shells, different points, electric field, right? And we talked about not electric field, gravitational field. I'm sorry, I'm repeatedly talking about electric field because the terms just, that is in the case of the electric field, the terms changes just like this. G m1 m2 by r, so it just changes into what? 1 by or k q1 q2 by r square. See, these equations are all similar. That's why I usually make a jumble around it. Sorry. Clear? Right. Now the next term which you have to know as well as not there in your textbook is gravitational potential. Gravitational potential energy is there, but gravitational potential as it is not there in your textbook. But I believe it is better to take first gravitational potential and then go to gravitational potential energy. Clear? Right. Clear? See, it is just like this one. Sorry. Suppose I have a mass m, right? So I told you it will be having a particular area around it where it will be exerting a force of attraction on another mass if it comes there, right? That we termed it as what? Gravitational field of that mass m, right? So similarly, there is another term which you have to know, which is gravitational potential. That is, so let's say this is mass m, right? So it is having an area around it where it is having maximum force at certain, or maximum force force it can exist, right? Gravitational force can be exerted by this guy, that we told it as gravitational field, right? Now suppose I want to bring another mass into this field, means I have to do some work, right? I have to do some work if I want to bring, because this guy might be doing another work now. This guy will be exerting a force, right? So along with that force, I have to bring another mass from an exterior section, means I have to do some work, right? That work, right, which I have to do is called gravitational potential, right? So let us talk about gravitational potential energy also, then you will understand the difference. So gravitational potential energy, this is there in your textbook, this one, right? Potential energy. I will talk about gravitational potential now. We'll talk a little bit about it more, and then I suddenly will come to the gravitational potential also. So definition part, etc., you can actually see in your textbook, but I will tell you in a layman language which is very easy to understand. See, that is, this is your earth, that is, this is the earth surface, right? Let's say this h1 is one height. Let's say I am having a mass m1 here, and there is a position here h2, right? I want to bring this mass m1. So this m1 will be having its own, this is capital M, that is a mass of earth, okay? So against this gravitational force which will be pulling this guy, right? This is gravitational force or potential energy, right? It is acting downwards, right? So against this force, I want to bring this mass from here to here. I want to bring this position, or I can say this is A and this B, means I want to bring this guy M1 from this position to this position, means I have to do some work, right? Actually, the work which I am going to do by bringing this M1 to this position from A to B, that much work is actually going to be stored in the mass M1 when it reaches B, right? That energy we term it as usually potential energy. This much is clear, right? So there itself I talked about potential energy, right? So what is potential energy of a body which is acting out of gravity? That is known as gravitational potential energy, right? Potential energy of a body acting out of force of gravity is known as gravitational potential energy. That is, suppose the position is changing, right? So position, initially it has a potential energy. Let's say it is mgh1, right? Now its potential energy will change to mgh2. So this potential energy change has been acting due to the work I have done to bring from this point to this point, and that work is actually stored here, right? So let's say I am doing a work w12, that is from this position to first position to second position. I am doing a work 12, means that 12 is actually equal to potential energy, final potential energy minus initial potential energy. Let's say this is V2 and this is V1. So V2 minus V1 is work done from moving this mass from this, or from here to here, right? We have already talked about it. Work done is equal to negative change in potential energy, right? You have learned in work energy, right? Just like the same thing, I'm doing a work from moving this body to this body from this position to this position, means I'm doing some work. That work is stored as a potential energy. So potential energy of a body due to the act of gravity, right? I'm acting it against this gravity, right? So this is known as potential energy. This is a layman thing to understand. Yeah, we go for derivation part also, how, and we will derive by this example itself, but I want to make something clear for you guys. Suppose this is a surface, or this is a mass, let's say m, right? So this mass is having a gravitational field here, right? So I want to bring, let's say, a m1 mass from infinity. Infinity means some very far point. So from very far point, I want to bring this m1 to this position in nearby to the gravitational field of this m. That work I do to bring this mass from infinity to the gravitational field of m, that is called gravitational potential energy. That is the easiest definition. Again, I am repeating, work done to bring a mass from infinity to the gravitational field of another mass, that is known as gravitational potential energy. Right? The work to be done against the gravitational force by an external energy, right? This is the external agency, to bring it from infinity to a present position without any change in acceleration. Right? Actually, someone asked you what is the definition. Gravitational potential energy of a body is the work to be done against the gravitational force by the external energy to bring that mass from infinity to its present position without changing its acceleration. That is known as gravitational potential energy. That is what you call it as gravitational potential energy. Right? So this is, let's say this is a capital M mass, so it will be very easy. And let's talk, this mass is m. Right? If I want to bring the small mass m from infinity to the and this work will be done by an external agency, right? So an external agency is doing a work to bring this mass m to some position, right, relative to this mass, right? So work done is done, that is called potential energy of that mass. Which mass? This mass. Right? The potential energy of a mass m brought from infinity, let's say this point is P, right? So I am going to bring this mass m to this point P, right? So potential energy of a mass m brought from infinity to the point P is depicted as U is equal to minus Gm m by r. Minus Gmm by r. Right? Clear? So what is, someone asked you what is the definition of gravitational potential energy? Work done by an external force to move a mass from infinity to a point, right, is called as gravitational potential energy. We have not reached, this is just an expression. We are going to derive this expression. I will tell you how. Clear? So you can usually it is U, it's a potential energy is always depicted by U, right? So earlier I wrote it as V. Why? I will tell you, right? Clear? It's because there you have to talk about gravitational potential also. Clear? This is very confusing point. So I hope you clarified what is potential energy. Potential energy is work done to bring a mass, not a unit mass, just a mass from infinity to a point. Clear? Right. So now comes, why did I write V, etc. So that V is actually representation of gravitational potential. U is for gravitational potential energy. Keep that in mind. U is for gravitational potential energy. V is gravitational potential. I'll tell you why. See, same as, right, capital M. Here, in place of m mass, I wish to bring a unit mass, that is 1 kilogram. Right? I want to bring 1 kilogram mass from infinity to, let's say, a point P. Right? So, again, I'm telling you, I want to bring 1 kilogram mass from infinity to a point P. That is the potential of capital M mass at this point. I hope you didn't understand. I am repeating again. There is a difference between potential energy and potential, right? So this is mass m. Let's say this is point P and let's mark another point Q. Right? So again, at infinity, very far, I am having 1 kilogram mass. I wish to bring 1 kilogram mass to at point P, and after some time I want to bring another 1 kilogram. Let's say there is another 1 kilogram that is also at infinity itself. Right? Both are at infinity. right? But Q and P are a different distance from M, right? This is center of mass. The difference or the mass is at a different distance from Q and P, right? So work done in bringing a unit mass from infinity to a point is called a potential at that point. I will term it as Vp. Again repeating, work done to bring a unit mass from infinity to a point P. Again, it is in the presence of M, right? That is known as potential at P, right? Let's say the distance here is R1. Let's say this distance is R2. Okay, so potential at P or P is known as minus Gm, because potential is due to only this guy, divided by R1. Now, what is potential at Q? Work done in bringing a unit mass from infinity to that point is known as potential at that point, or VQ. Potential at Q is work done in bringing a unit from mass from infinity to the point Q, which is at a distance R2 from the source mass, which is capital M. So VQ is equal to minus Gm by R2. Clear? So what is the definition of potential and potential energy difference? Potential is work done in bringing unit mass from infinity to a point, right? Potential energy is work done in bringing a mass, not a unit mass, any mass, from infinity to that point. Clear? So difference, I hope you understood, right? So now we are going to talk about in the case of what? In the case of we are going to derive the expression, right? So this is our ash, this is our earth. So derive the potential energy, okay? Gravitational potential energy derivation. So let me bring this guy downwards. Okay, right. So let's consider there is a point A here, there is a point B here. Let's say point A is the height h1 from the ground and B is the height h2 from the ground, right? I wish to bring A from this position to this position. I want to bring an object. So obviously I am doing a work, right? So I'll write it as what? Work done. Let's say work I am doing, okay. Work done is equal to what? Potential energy change, right? So mgh2, that is, sorry, yeah, that is work done, okay, minus mgh1, right? That is at B, and A is potential energy. Work done is equal to change in potential energy, right? That is equal to, what is mgh2 actually? mgh2, that is the potential energy, right, at h2 height, which is h2 height, which is B, right? I'm sorry. Let's say I want to bring a mass from A to B, so we require two positions, right? So let's say this is A and this is B. B is at a height h1 and A is the height h2 from the surface of Earth, right? So this from the surface of Earth, okay, right? So this much is clear off. Clear? So work done, right, is equal to force into displacement, right? And force is your weight, right? Let's say mass M is to be brought, right, from A to B, right? So this is mass and it is moved from here, right? So it is mg. What is the displacement? h2 minus h1, right? This is h2 and this is h1, so h2 minus h1 is the displacement, or I can write it as mg h2 minus mg h1, right? What is mg h2? That is the potential energy at height, right? So I will write it as potential energy at A minus potential energy at B. So it is like this, right? This much clear? So that is the work done while moving a mass from A to B, right? Now we know that G is not constant. Acceleration due to gravity is going on changing, right? right? So let's say this is the first position, right, and this is second position. Let's say this is r1 vector and this position is r2 vector, right? So work done to move from first position to second position, right, is from r1 to r2 fdr variable, right? So that is equal to integral r1 to r2, right, gm m divided by r squared. That is a force experienced by this mass due to this guy. Let's say m is the mass of earth, so gmm by r squared into dr, right? That is equal to minus g into small m is a constant term, so I have 1 by r squared integral r to r1, right? 1 by r squared integral is 1 by r, right? So this minus gmm 1 by r, then I will suffix upper limit, that is 1 by r2 minus 1 by r1, that is lower limit, right? Clear? That is equal to minus gmm by r2 minus gmm by r1, right? That is equal to, what is gmm by r2 and what is minus gmm by r1? I just told you that is the what? This term is called potential energy at distance, right? I hope you remember I talked about the expression for potential energy, right? Minus gmm by r, right? So minus gmm by r2 is the potential energy at the position vector r2. So W21 is equal to potential energy at position r2 minus potential energy at position r1, right? Clear? So I can just write, suppose right, suppose I can generalize this equation. How? Suppose in this entire section, suppose there is no intermediate step, right? Suppose that this b is not there. I am going to bring this element or mass m from this topmost position to surface, right? I am bringing here to here only, right? So that means I can eliminate this guy. Why? Because there is no position r1, guys. Or I can say, or any position, I can talk about this position. I'm going to remove, let's say, this position. That's better, because in the previous figure, in this case, I talked this as the initial position and this as the second position, right? And I told this is the r1 and this is r2, right? This is r2 and this is r1, right? Let us remove the intermediate position, means this position I'm going to remove. So I'm just going to bring the object mass from this position to ground, right? So this goes off, right? So I can just write the general formula of work as what? Just the potential energy, right? That is this u r1, or I can just write it as, what is the expression for u r1? Just the position or the potential energies equation. We have derived it initially. It's a potential energy at any vector position r is equal to minus gmm by r. Potential energy at any point. Now someone asks you the potential. That means you are not bringing a small m mass, you are producing a 1 kilogram. So the equation becomes gm by r, and in place of u you are supposed to write it as v, right? So what is u of r? That is a potential energy minus gm by r. That is a work done in bringing a mass m from infinity to a point, right? That is minus gm by r. And if you are bringing a 1 kilogram or unit mass from infinity to that point, then that becomes the potential at that point. This much clear, right? That is, again, I am repeating because this is very important to understand. This is the surface of earth. You are having a point here, let's say it is at r distance from this capital mass earth. So I want to bring, if I am bringing a small mass m from this position to this position, then I am doing a work, right? So that work is due to the change in potential energy, right? So here I am bringing the potential or the mass from this position to the center of earth, so no intermediate point. So I am bringing a mass m from infinity to this mass, right? So I will write the potential energy U is equal to minus g m by r, right? Now if I am bringing place of m, I'm bringing 1 kilogram mass from this point to another point, which is in the presence of this capital M. So it becomes V is equal to minus g m by r. Clear? I hope this much is clear. Right. In HCA Verma, there is a very good example to properly explain the entire thing of potential energy. See, same example they have taken in your, not from your textbook, guys. It is from HCA Verma. Okay, this is a position A, position B, and this is our hero Earth. Okay, so let's say this is point infinity. So when you bring, let's say, a mass m from infinity to this point A, this A is in the influence of this capital M mass, right? This in the gravitational field of this capital M. So at point A, when you bring a mass m from infinity to this point A, you get that, or you store that work which you are doing from bringing from infinity to this point A as a potential energy at A, that is UA. Now infinity, I'm bringing a mass m from infinity to this point B, right? So I'm doing some work, right? So I'm bringing mass m from infinity to point B, means I'm doing some work. That work is stored as potential energy at B, so I will take it as UB, right? That is UA and that is UB. Clear? This much clear, right? This is the best example they have talked about in the HC Verma textbook, right? So you got UA and UB, right? Now you are bringing that mass, let's say m, from this point A to this point B, means you are doing some work, right, against the potential energy difference. That's why you will write work is equal to UA minus UB. Simple as it is, right? This is not your textbook have explained, that why I explained in your textbook point of view. Clear? So for me, this is the best example of understanding. Clear? Clear? Right. So when you're bringing a mass from infinity to a point, that is stored as what potential energy of that point, right? So in the case of potential energy, the influence or the source mass as well as the mass which is brought is very important in the case of potential energy. But in the case of potential, only the source mass is important, right? In the case of potential energy, it is minus gmm by r, what you are bringing and in whose presence it is important. Whereas in potential, minus gm by r means only the source mass is important, because you are bringing a 1 unit mass, right? So it is not important. Clear? Right, this is the best example. Now another section which I forgot to mention is we had two equations for g, right, for height, right? G dash, that is acceleration due to gravity at a height, that is gh is equal to 1 minus 2h by re, right, into g, and you had gh is equal to g divided by 1 plus h by re whole square, re or r, just r. Right, so there comes a question when to use which equation, right? So keep that in mind. If you are bringing the mass to a height which is very, very small when you compare to the radius of Earth, that is, this is the Earth, and you're just, then the radius of Earth is 6,400 kilometer, right? So if you're bringing the mass to another, say 1 kilometer height, you are bringing a mass, means this height is very small compared to the radius of Earth, right? In that conditions, it is better you use this equation, right? When you are bringing an object to a height which is very, very small when compared to the radius of Earth, that is when h is very, very small when compared to radius of Earth, use this equation. Whereas if you bring the mass to very high height, right, very high height means this is 6,400 kilometers, you're bringing it just suppose 7,000 kilometers or more than 6,000 kilometers, it is better you use this condition. When h is greater than re, use this equation. Keep this in mind. Okay, that's the question. Numerical questions will be like this, that is, you are bringing the mass to a position double the radius of Earth or equal to the radius of Earth. In that conditions also, it is better you use this equation. But in the condition where you brought, or in the question it is said that you have brought the object to 3 kilometer, 10 kilometer above the Earth's surface, use this equation. I forgot to mention it during the live class. Clear? I hope this much is clear.